Welcome to today's Research Pays Off. I will hand it over to our speakers, Emin, Kutay, and his students.
All right, thank you so much. Really appreciate it. Let me go ahead and share my screen. Can you confirm
great.
you can see?
Yes, looks great.
Okay. Okay,
Thanks.
awesome. Thank you. Well, thank you so much for coming to this webinar. We're going to be talking about flooding. We're going to be talking about modeling flooding in terms of mechanistic empirical methods, and look at the effect of flooding on pavement performance in the network level, pavement network level, individual and pavement network level. Before I start, I'd like to acknowledge my co-authors, Farhad and Mike. This webinar is going to be presented by myself and Farhad. He is right next to me. So he's going to take over after a certain number of slides and present some of the work that he's done on this project. So I will go ahead and start with some introduction on the topic. I think I see someone unmuted. You might want to mute yourself. So the reason for this particular project, a particular study, is climate change. So the effects of climate change is clearly visible in many aspects. We know that global temperature is rising. There are changes in precipitation patterns. When you look at the coastal regions, there are changes in sea level. And more importantly, we are seeing more and more extreme weather events. It could be heat waves, wildfires, intense precipitations, storm surges, floodings, flash floods, hurricanes, and all these extreme events that are not expected in a pavement's life, they can cause significant damage. And we would like to know that. We'd like to know how much damage these events can be causing on the pavement network and what we can do to mitigate that. Our particular emphasis, our particular focus is flooding. So you're going to be hearing mostly about the effect of flooding on pavement performance. If you look at the flooding events, if you look at NOAA website, and you'll see very good data there about the trend of flooding and the frequency of the flooding and how they increase. And this particular slide, if you look at this particular little graph right here, it shows a clear increase in relative sea level, and accordingly, you're seeing the high tide, the flooding that is caused by high tides, the frequency and the number are clearly increasing. And this is just one example. And flooding can cause many different problems. One of them is traffic disruptions, obviously, road closures, detours, and they all have certain effects on pavement performance. The flooding itself can cause damage to pavement layers, and it can also have an effect on the economy because of the disruptions in the transportation. If you look at this again, a NOAA website, and if you see from 1980s to all the way to 2017, the amount of flood, all the natural disasters, and how they are increasing, there's a definitely an increase in the cost of the extreme events and how we respond to them and how we deal with them. And if you look at this data, roughly 63% of all the natural disasters are because of flooding. So clearly, flooding is a major issue. And there is a lot of good research on this area as well. So in this particular slide, this picture is coming from a reference from Lu et al. They had a very good study on analyzing what are the components of flooding and how these components affect the pavement in general. So you might have a river flooding, which is something that we know very well. This is like sustained and intense rainfall can cause flooding in the riverbeds. You might have an extreme heavier, extreme event or flash flood can cause flooding. You might have coastal flooding. You might have dam failures. We had these in Michigan. You might have groundwater flooding that can be caused by the problems in the aquifers, and more importantly, when we have drainage in the pavements, it might, if they are damaged or if they are not sufficient, they can cause all sorts of flooding. So there are many aspects of flooding as described by this reference, and in the same reference, you will see a very interesting way of explaining what are the different potential impacts of flooding. The first one is the catastrophic failure. So you might have the whole pavement essentially failed and then unusable. So that's a possibility. You might have a case where the flooding happens and it seems fine, but because of the changes in the internal structure of the layers, you might have accelerated damage happening and reducing the overall life of a pavement. You might have um, a partial damage that's happening during the flood event, but then the pavement might recover back to its original case and might continue to live its life in the same kind of a rate that it had in the past, like shown in here. The maybe more realistic case would be this last portion, which is you might have a significant damage during the flooding event, and because of that, you might have an accelerated damage, or the rate of the damage can increase with time. So this is the part that the models that we are going to discuss, and we're going to be telling you about UPDAPS. We're going to talk about that particular model and how we are handling. So we are kind of focusing on this very last condition. So what are the different mechanisms of damage? One is obviously the drainage systems. As I said, there are a lot of very good literature on how the flooding can affect the pavements. You might have drainage problems because of flooding. You might have problems within AC, the asphalt concrete layer. If you're talking about a flexible pavement, so you might have moisture damage problems in the long run. These are a little bit studied quite a bit in the past. One of the things that hasn't been studied that much is the effect of water on already damaged pavement or cracked pavement. So this can have, you might have a significant problem in those cases. So the most of the damage is known to happen in unbound layers. So this is very well known. So unbound layers, the resilient modulus can decrease because of flooding. When you have a resilient modulus decreasing of an unbound layer, the strain for a given load is going to increase, and its bearing capacity might decrease. And as a result, its support and the stress distribution impact of a truckload on the overall pavement structure can change. It can change to a condition where that you haven't designed for. And when you have more strain in the base and in the shape of the load, you might have more load on the subgrade, and then you might have subgrade failures accordingly. And then subgrade itself might have its own problem. So the effect of flooding on unbound layers is very well known and very well established. We know that flooding can affect unbound layers significantly. Lesser known fact is when we have more and more extreme events and flooding, you might have changes on traffic patterns. So if you have a high volume road like this, if it gets flooded and it can't be used for a certain period of time, detours can cause significant damage to a road that's right next to it. It may not be flooded, but it might experience the loads that particular pavement is not designed for. Now, that can cause indirect effects on the neighboring roads. So that could be another issue, and such a thing has been reported in the past. So if you look at the mechanistic methods, such as MEPDG, the impact of moisture in the layer properties is very well established, and there are equations inside MEPDG that can modify the resilient modulus depending on the moisture conditions. So this particular fact is obviously very well known. And some studies show that when you have a partially saturated pavement, you might have about 40% reduction in MR. When you get closer and closer to saturation, you might have even up to 80% reduction in resilient modulus. So these are significant effects that can affect the overall pavement structure. Um, the last slide I would like to talk about is the what happens after flooding and how the rate of flooding, the rate of recovery changes depending on the characteristics of the layer. So this is another area where people have made research, have done research, where the type of soil, type of grain size distribution, they all affect on how the recovery period, how long it takes for the pavement to recover. So all these aspects we have been studying, and we have started developing mechanistic models. And we're going to be, my student Farhad is going to be presenting those models and some of the findings that we found.
Okay. Hello, everyone. So I'm going to continue on the presentation. So I'm going to, from this point, I'm uh, moving, if I can. Okay, so we're moving to the methodology and the results of our study. So in the methodology part, the overview of the methodology includes the data sets that we are using and the developed tools that we developed here, the computational resources and the results. So in terms of the data sets, we are using three main data sets for this purpose. The HPMS dataset, which is the national level data of the big data set of the pavement sections all over the United States. We have the NUA dataset that has the flooding records and the historical weather data that is used in the ME pavement analysis tools. But more importantly is that UPDAPS, that is Unified Pavement Distance Analysis and Prediction System. So we developed the UPDAPS here at the Michigan State University for FHWA, and this model is some mimic of the MEPDG with the improved features. And we are modifying the UPDAPS to develop the UPDAPS-Flood to incorporating the flooding events. So eventually, the data sets that we are discussing about, they are inputs to the UPDAPS-Flood, and then we are using the computational resources like our National Lab Track Facility or the Michigan State High Performance Computing Centers, and we are using these resources to get the results on the project level and the network level. In the next slide, I'm going to dig deeper into this methodology. So first, let's talk about the HPMS. So HPMS is a big data set of the more than 128,000 pavement sections all over the US. You can see the spatial distribution on this picture here. So we are using the HPMS for creating inputs for the UPDAPS to run the UPDAPS and UPDAPS-Flood models. So in case that we need more information that they are missing in the HPMS, we are using the NAPCOM, HERS, and LTPP datasets to complete the inputs for the mechanistic-empirical design. For this specific study, we are extracting 7,665 flexible pavements from HPMS in these regions. And you can see we have the coastal line of the Gulf of Mexico, about 3,000 sections there. We have Minnesota, about 500 sections there. And we have California with about 4,000 sections there. So we have total of 7,600 sections. The reason that we are choosing these regions is because different flood patterns they have. The flood patterns we are targeting is from sea level rise, from high precipitation, and also from flash floods like those we have in the Minnesota most. So the next source of data is the flooding data set. So we are going to use the NOAA data set for the storm events. You can see this is the website that you can choose a date and then export all different of event types. So we are extracting the floods, hurricanes, and the flash floods for the uh, from 2002 to 2022, which is 20 years of pavement design for all HPMS sections. But the only point here I want to emphasize is that the resolution of data is by county. So the assumption that is forced to us is that all pavement within a county are subjected to the corresponding floods that is recorded. So it might not be a best assumption, but the high resolution may be available in the new version. So as soon as it is available, we can implement it into the UPDAPS-Flood as well. So here is a very quick example of the data that we are extracting from NOAA. So you can see you have the county name, you have the beginning time and date, and you have the event type and end date. So we are analyzing this kind of data in the CSV format, and then we are assigning to each section and analyze the UPDAPS plot. And here is the data we are extracting for our study. So for 3 regions, you can see there are about 2,000 flood events on the 200 counties. The data is from August 2022 to 2022. And then we are defining highly flood sections as sections that have more than 30 days of inundations. So these are the real data. So some sections might not have enough, a significant number of inundation dates. So that's why we are defining these highly flood sections, and there is only 24% of the sections which is highly flooded. And you can see this in the results and how they are changing our results. The last thing is the historical weather event. So it is very familiar in the MEPDG as well. So we are using the historical trend of the temperature, precipitation, humidity, wind speed, and cloud cover. And these are the inputs to the EICM. And we have our own model. We are calling it MCLIME, which is climatic model, to forecast the future climate. So these 3 are the main inputs to the UPDAPS. But more importantly, this slide shows the UPDAPS, which is the Unified Pavement Distress Analysis and Prediction System. And this is a mechanistic empirical pavement analysis tools. You can see that we have it for flexible pavement, rigid pavements, and composite pavements. So it's a very broad model to analyze the pavements and for analysis and design. There are the UPDAPS initially based on the MEPDG formulations, but we did lots of improvements into the model. So 3 of the main improvements that I want to emphasize today. The first one is the fatigue cracking model. So we are using the VCD theory to predict the fatigue cracking, which is previously in the MEPDG, they are using the simple Marner's law. So this is one of the major modifications to the UPDAPS model compared to the MPDG procedure in pavement ME. And then we have changed the pavement response model. This is another significant change. So unlike MEPDG, which is do the simulation at only one load level and do the extrapolation based on proportion to the load levels. So we are using a study by Siva Santa, and then we are doing the extrapolation using 3 load levels. So that's increased the accuracy of the critical pavement responses and significantly increased the accuracy of the responses and calculated the damage. And also we have a significant changes in the climatic model. So the computation of the downwelling short wave, up downwelling long wave, and upwelling long wave radiations are updated. And also we are including the sunrise sunset times to calculate the net flux radiation distributed over the daytime, which is the previously implemented in the EICM. So we have plenty of other improvements as well, and these are just some examples. So I want to emphasize on NAPCOM as well because UPDAPS is implemented into the NAPCOM++ model. So NAPCOM++ is a graphical user interface that's designed to easily run the UPDAPS over thousands of sections, and it is very user friendly and it's very easy to use. So if you think of UPDAPS as the analysis engine of the model, so the NAPCOM is the whole truck. So it's like we are using NAPCOM for usually we are using it for perform a highway cost allocation studies. And for that, we need to run the UPDAPS many times, and that's how the UPDAPS is implemented in here. So for many of our runs, we are just simply using the NAPCOM, and it's very user-friendly, and anyone can do it. So it's very easy to run the UPDAPS through NAPCOM, actually. So the next thing I want to emphasize from UPDAPS, so UPDAPS is the baseline model that we developed here, and then UPDAPS-Flood is the UPDAPS version we modified to incorporate the flooding effects in a mechanistic empirical method. So the UPDAPS is using the incremental damage accumulation approach. So it is the same as the MEPDG, and and this is a very schematic illustration of how it works. We have climatic input and traffic going with the material properties to the mechanistic analysis, and then using the transfer function, we are predicting the performance. So now the modifications to make the UPDAPS flood are four main modifications. The first one is the modification in the analysis period. The reason we are talking about in the next slide. The next thing is that the resilient modulus of the unbound material. So the material properties is changing due to flooding, and we are incorporating that. The next thing is the distress model coefficients. So due to the flooding, the behavior of the saturated unbound materials can be changed, and we are incorporating that into the model by coefficient changing the coefficient of the rotting model, for example. So it changes, it can take account for the accelerated, for example, accumulation of the damage. And then the last one is the modification in the traffic. So let's dig more in this four modification types. So the first one is the modification in the analysis period. So the MEPDG usually uses, or the EICM model in the MEPG. It uses 5 quantiles per month. So the analysis is per month, and then we are doing a statistic analysis and find 5 quantiles of the representative quantiles of the temperatures, and we do the analysis based on those 5 quantiles per month. But the flood durations can be hours and days, so that's why the monthly analysis is not very realistic. So that's why we are using the daily analysis for only the months during the flood events and the post-flood events. So whenever you have a flood event, we are changing from the monthly analysis to the daily analysis to increase the resolution of the model. And then it is keep doing the daily analysis during the post-flood time up to full recovery as well. So this is the main, this is one of the main changes we are doing to make the UPDAPS flood model. The next one is that the modification of the unbound layers resilient modulus. So we know that the intrusion of the moisture into the unbound layer due to the flooding can reduce the resilient modulus. So with higher moisture, you are having the lower resilient moduli. And then during the post-flood, because the excess water drains and going out of the pavement structure, so the saturation levels recover to the normal levels, and then you have, and some studies shows that statistically the full recovery can be expected. So the resilient modulus goes back to the initial level. And we are assuming different passes. So we are considering that how this recovery rate is happening. So it can be linear, it can be delayed, it can be very accelerated. And that's how, and the duration and rate of the recovery is just a function of physical properties, drainage properties. So there are lots of things that affecting that. So based on the literature, because we don't have enough information about the gradation and the permeability of the section. So we are just assuming a 20 and 60 days of recovery time for base and subgrade material. But the UPDAPS model is actually capable of doing any other arbitrary number. So for the recovery time, if you have more detailed information. So this is what we are using in this study. The last one is the modification of the traffic. So the traffic pattern can change after flood due to the, for example, heavy trucks for debris removal. So you have higher load levels, you have emergency vehicles, you have detours. So as Dr. Kutay just said earlier, so these detours can just detour the traffic loads to the pavements nearby that they are not designed for that amount of load. And also if there is a road closure on other loads, so the detours can bring the traffic load on the section that we are that is after flood. So this is flooded and is after flood. So we have this example in after the Hurricane Katrina and Rita. So it is reported that the heavy debris hauling trucks caused damage to the whole network. And in UPDAPS flood, we have this option to take a new set of traffic inputs, which is axle load the spectra, double ADT, and for example, everything, person truck distribution, everything. So you can enter those inputs, but because of the lack of the availability of the data for during flood and post-flood. So for now, we are just using a factor of 2 for ADT using the used in the major floods like hurricanes and major floods, and the factor of 25% increase for the flash floods. And this is going to just compensate for the effect of heavy trucks of debris removals and the detours and the high loads that are applied to the pavements after during the post-flood time. So when we develop the UPDAPS-Flood, so we are thinking of the validation of the model. So how can we validate the model? And the performance information is very limited, so we don't have that much of the performance information to do the calibration. So that's why we are using an indirect way to validate our model. So the way is that after Hurricane Katrina and Rita, it has been reported that 20% reduction in the structural number has been reported in Louisiana, New Orleans in Louisiana. So after we have this data, we are going to HPMS and see that there is 18 sections in New Orleans area, and we are model these sections with the UPDAPS-Flood model. So for this purpose, we only model the Hurricane Katrina and Rita, and we model that with the UPDAPS-Flood, and then we calculate the delta IRI due to these two hurricane events. And then we have the delta IRI from the UPDAPS-Flood. On the other hand, because these models are designed by the ASHRAE 93 method, and we have the structural properties and everything and traffic and everything, so we are using the ASHRAE 93 method approach, and then we change the structural number, we reduce it by 20% and calculate the delta PSI, the Pavement Serviceability Index, corresponds to that 20% loss of the structural number. And then we convert that delta PSI into the delta IRI using the conversion methods in the literature. And then we are for these 18 sections, you can see we plot the data, and you can see the median, although the ASHRAE 93 shows a higher variation into the variability in the results, but the median values are very consistent, which shows that the delta IRI predicted from the UPDAPS-Flood is matching with that is coming from the actually FWD testing and the actual observation in New Orleans, Louisiana. So that's how we are doing some indirect validation for the UPDAPS-Flood, but up onto the availability, we can do the better calibration studies as well. So the last thing I want to talk about is the computational resources we are using. So each UPDAPS-Flood runtime can take between 10 to 15 minutes and even more. So it depends on the pavement structure, it depends on the traffic, it depends on the number of floods, especially because it changed the analysis from monthly to daily. So it is a very big variation of the runtime. So we are designing the UPDAPS-Flood to be compatible with the parallel computing, and we have two computational resources available to us. We have MSU HPCC with about 1,000 CPUs at the time they are providing, and we have the Argo National Lab, which gives us even more. 3,000 CPUs can be available to us. So all 7,665 sections that we are running for this study can take only less than 4 hours in even MSU HPCC, which means the average runtime is about 2 seconds per section, and this is amazing actually. So you can run different scenarios. You can run, for example, different and in a very short period of time, and this is a very good compatible capability that we have here to run on the network level for the pavements. So now let's talk about the results. So these specific results show the project level of the results. So you run the UPDAPS for a specific section. For example, here I showed that for Florida 806 section in the HPMS, it has 2 inches of AC and 8 inches of granular base located in Miami, and it has 9 major floods with 54 days of inundation. So in this figure, you can see the blue dashed line shows the UPDAPS one without implementation of the flooding events, and the thick red line shows the UPDAPS-Flood results, in which you can see these jumps. Okay, so if you can see my mouse cursor, you can see there are little and big jumps here and there, and these jumps actually shows the flooding events. So we have 9 major flooding events in this for this specific section, and you can see how they are affecting the rotting here. Next figure shows the effect on the fatigue cracking, and finally we are using the IRI. So this figure shows that on the IRI, which is a combination of actually rotting, fatigue cracking, thermal cracking, and everything. So that's why we are more interested into the IRI. The reason is that it's combination of all different type of distresses. Somehow it's average them, and then we can define the resiliency metric for the network level analysis. So this is a project level results. You can see that the blue dashed line, for example, if you don't have any flooding, you are expecting about 120 inch per mile IRI, for example, for this section. But when you have the flooding data affected your section, you will see that the amount of the IRI increased, for example, up to 140. And then we are designing a resiliency metric to be used in the network level. And this metric is simply defined as a reduction of pavement service life. And we are using IRI because it's a combination of all fatigue and rotting and everything. So, for example, in this section, if you have about 120 inch per mile IRI at the end of the service life without flooding, so now that you have flooding, this amount is corresponds to the pavement life at 17 years. So which means you are losing 36 months of the pavement service life. Okay, so that's how we are defining. That's how this resilient metrics we are defining and use it. And the same metric has been used in the literature as well. So now let's talk about the resilient metrics in the network level. Now that you have the project level, you can talk about the network level as well. So we had about 7,665 sections in 3 regions. We have Gulf of Mexico, California, and Minnesota. So you can see that this bar graph, the blue one shows all sections, and the yellow ones or orange ones shows the highly flooded section. If you remember, the highly flooded sections are the pavement sections with more than 30 days of inundation during the service life. So first thing you can see is that the and pavements in the Gulf of Mexico experience about 2 times higher damage. So the more the resiliency metrics means that more damage is applied to your pavement, so you lose more months of the service life. So the pavements in the Gulf of Mexico has about 2 times higher damage, and it is well aligned with the NRRA flood records. The reason is that we had more frequent and more severe with more days of inundation. Flood happens in the Gulf of Mexico. So that's why the results make sense. And also, the next thing you can see is that the pavements in Minnesota are experiencing higher damage than the pavements in California. When we checked that with the flooding records, we saw that the pavements in the Minnesota have the pavements in California actually experience more frequent and severe floods. But the reason that they are having a better resiliency against flooding, which means that the resiliency metric is lower, so they lose less months of the service life. When we are actually going and dig more, we saw that the AC layers in California was averagely about 2 inches thicker than those in Minnesota. So that's one of the reasons that why they are more resilient against flooding, although they are experiencing more severe flood. And this is one of the corrective actions that we are investigating later for the whole network as well. The other thing that you can see here is that the highly flood sections, for example, if you compare the yellow ones with the blue ones, the bar graphs, you can see that the highly flood sections in Gulf of Mexico has about 1.5 times more damage, and in California, the highly flood section is about 2.5 more damage. So if you have a highly flood section, you are definitely expect more damage to the from flooding, and you can definitely see that in this graph. The reason that we don't have any yellow bar graph for the Minnesota is that because we are mostly have the flash floods there, and we don't have the highly flood sections with more than 30 days of inundation in the Minnesota recorded between 2002 and 2022 by NOAA. The next thing I want to show is the resiliency maps that shows the spatial distribution of the resiliency metric. So these maps is very good to have an insight about the whole pavement performance in the region of the interest that you are looking at. For example, in this particular resiliency map for the Gulf of Mexico, you can see that the coastal line has a relatively higher resiliency metric with which means that they are losing more months in the service life. And this is more expected because they are in the coastal line, and then because of the sea level rise, and for the coastal floods, you can see that you're seeing much more flood damage to this to the pavement in this area. But the very important point, I really like this slide. The reason is that you can see some, for example, all these green dots here, you can see some blue dots here and there. So this means that although that they are experiencing a very severe and, for example, more frequent floods, still you might have some pavement sections that have a better integrity in terms of structure, maybe thicker, maybe, for example, more strong, and then they are performing better against flooding. So that's a very good, this resiliency map can give you some insight even in the bigger scale of the regional or by counties you are looking, or to identify the flood prone regions, or it can give you some insight of which pavements perform better and which are not. So this is one other product of the UPDAPS-Flood that you can run it in parallel for too many sections, and then just produce this kind of resiliency maps as well. So after that, we are running some sensitivity analysis to investigate the effect of different parameters, actually different significant parameters on the results of the UPDAPS-Flood. So the first thing we are investigating is the amount of reduction in the unbound layer moduli due to the saturation. So we are using three different levels: 30% reduction, 50% reduction, and 70% reduction. And you can clearly see that the sensitivity of the model to this is quite significant. So higher saturation levels may cause more reduction in the resilience modulus, and that reduction in resilience modulus can cause higher higher reduction in the pavement service life. Okay, so that's why the model is quite sensitive to the amount of reduction in the pavement life, and when we have more data on in terms of lab studies and everything, so you can actually have better accurate models to predict this amount of reduction in the resilient modulus. So the next thing we are evaluating the sensitivity of the model to the recovery function. So if you remember, we are investigating three different passes. It depends on the drainage properties and the material properties, especially permeability. So you can have an accelerated recovery, you can have some delayed recovery, or a linear path which average those two. So we are running the models using all different recovery functions, and then you can see that the results are quite sensitive to the recovery function as well. So it is very important. So this is highlights the importance of subsurface drainage. So although you have a severe flooding in your sections, if you have a very good drainage system, so which means that you have accelerated recovery like this, so you can significantly reduce the amount of losses in your service life. So you can reduce the resiliency metrics of your network with just providing the better drainage properties for your system. The next sensitivity analysis is the sensitivity to the rotting coefficient. So the K1 coefficient in the rotting model is a linear multiplication to the rotting model. So although there is more study needed to investigate this effect more to the behavior, rotting behavior of the unbound materials under the saturation and near saturation and partially saturation conditions. So we are changing this from 1.25 multiplier to 2 to see the effect and so to see the sensitivity of the results to this K1 coefficient. And as you can see, the sensitivity is quite high. So it is very important to recalibrate the distress model at high saturation levels. So you need to run the repeated load permanent deformation test at different saturation levels to actually know how to choose this K1 coefficient, because the model results shows us a relatively or quite big sensitivity to this K1 coefficient. Uh, after this, after running the sensitivity analysis, in the end, I want to emphasize some applications of the UPDAPS-Flood model. So first application is the pavement design. So now that you have this model available, the UPDAPS-Flood, so you can use the UPDAPS-Flood to design the pavements to be more resilient against flooding. So if you know some historical trend of the floods from the NOAA website, so you can use that to predict the future, like what we did for the air temperature in the EICM or something. And then for a given scenario of the flooding, you can run the UPDAPS-Flood and change, for example, here we are only changing the thickness of the AC layer. So we are changing the thickness for the same FL 806 section from 2 inches to 6 inches. And you can see this thick black line shows the results without flooding. And then this dash red line shows the results, the IRI prediction with flooding when you are changing the thicknesses. And then based on this analysis, you can increase the AC thickness so that finally you got the same, at the end of the 20 years, you got the same amount of IRI from your section. So this is kind of a corrective action that is well, established in the literature as well, the increase of the AC thickness. And then you can use the UPDAPS-Flood for design your pavement to be more resilient against flooding. And it is not limited only to the AC, increasing the thickness of the AC. So actually in UPDAPS-Flood, you can change any input parameter to the for the pavement analysis, and you can play with those and find the best optimum design for a pavement section to minimize the cost and maximize the resiliency against flooding. So the same thing is shown in this figure. So for this specific 806 section in Florida, if you increase the AC thickness from 2 inches to 4.6 inches, because you have the 9 major floods with 54 days of inundation, which is quite high. So initially you have 36 months loss of the pavement service life. So if you increase it to 4.6 inches, you can just make the resiliency metric 0, which is the best case scenario, which means the pavement is fully resilient against flooding. And also you can analyze different scenarios as well. For example, if you increase the thickness from 2 inches to 3 inches, so you can reduce the 36 months of service life, loss of service life to about 23. So it's a quite impressive improvement as well. But this is one of the main applications of the UPDAPS-Flood model in the project level. In the network level, we did the same thing. So from the literature, we saw that the higher increasing the AC thickness can alleviate the critical structural responses, and we saw that in our results as well, as we saw the results for California, that they have a higher average, higher AC thicknesses, so they have the lower, so it causes lower amount of the reduction in service life. So what we did here, we run the whole network, so the whole thing with 7,665 sections, but we are artificially increase the AC thickness for 20%. So when we do that and we run the UPDAPS again, you can see that this blue bars shows, for example, for Gulf of Mexico, California, and Minnesota, the blue bar shows all sections with the actual AC thicknesses coming from the HPMS, and this yellow bar shows when you are increasing AC thickness for 20%. Okay, so then you can see a significant reduction in the significant improvement of the resiliency against the flooding can be seen when you increase the thickness of the AC layers only by 20%. For example, in the Gulf of Mexico region, the pavements averagely shows a 63% reduction in the resiliency matrix, which means that there is about 63% improvement of the resiliency. And in the California, it's actually 100%. The reason is that California pavements are already the ones in the HPMS. The California pavements are already thick enough. And then when you increase the thickness by 20%, you totally eliminate the problem with flooding based on this result. So the pavements can, and can be more resilient against all the flooding scenarios records that we are extracting for the California region. And for the Minnesota, this value is about 81%. So this result shows that the 20% increase in the AC thickness that is suggested in the literature is actually working, and it actually our results from UPDAPS is well aligned with the literature that the 20% increase in the AC thickness is actually significantly works. this graph is for all sections, so I just regenerate. We just regenerate the graph for highly flooded sections, and because we don't have any highly flooded section in Minnesota, so we don't have any bar graph here. But you can see for if you have a highly flooded sections, although the resilient metric is higher, which means that higher months you are losing in service life, but still increasing the 20% can cause about in Gulf of Mexico can improve the resiliency to the flooding for about 50%. And in California, because we have thicker pavements, again, the resiliency totally worse. But in still in Gulf of Mexico and still for highly flooded sections, we have about 50% improvement as well. And I think this is my last slide. So this to the project design and the network level is one of the applications of the UPDAPS model. So before I finish my slides, I would like to talk very briefly about the future steps. So here at Michigan State University, we are developed a model for the GeoGrid GeoGrid modeling and nonlinear pavement structural modeling. So our next step is to implement that into the UPDAPS-Flood as well, and then we can evaluate the effect of GeoGrid reinforcement instead of, for example, AC layer thickness increase. So we can investigate the effect of GeoGrid reinforcement as a corrective action against flooding as well. So there are lots of laboratory works are also in progress to validate and verify the inputs to the UPDAPS-Flood. But in this presentation, we have this UPDAPS-Flood model. Thank you. Okay.
Thank you.
Sure.
I am going to check on, looks like we do have a comment here. And so it looks like there's a presentation link for a possibly a similar topic at Texas A&M. At this time, if you have other questions and you want to raise your hand, it looks like I've got a hand here. Daniel.
Yes, this is Daniel from Solmax. Very interesting topic and nice presentation. I have a question about the unbound material properties that you mentioned. One of the most important effects of flooding is how it changes unbound material properties that also affect AC layer properties in flexible pavements. You said you considered the resilient modulus reduction based on the flooding. Maybe you mentioned that and I didn't realize, but when you have flooding or any types of moisture moving through your pavement structure, you need to have a system dynamic, with a couple of models to be able to capture the true effect of moisture. Like you have hydrological model to determine the saturation in your materials based on the material type, layer thickness, porosity, infiltration, groundwater level, etc. And then you need a geotechnical model to calculate the resilient modulus based on the saturation level at that specific time, and it will change over the time. So you could have fully saturated soil at that time, and like 10 hours later, it's partially saturated or unsaturated. And soil or unbound material properties, and the way you can determine the properties at different times are really different, very different. Exactly. So if you were able to capture the state of saturation at different times, then you need a pavement response model to translate your time and moisture dependent calculated modulus, resilient modulus, to, let's say, like surface deflection or any mechanistic responses in your pavement structure. So my question is, did you have a dynamic model for unbound material to capture the properties at different time and different saturation condition, or you just use the equation that they had in the literature to calculate the unbound material resilient modulus based on different saturation level?
I think that's a wonderful question. Okay. We are in the same room with my students, so I'm trying not to have the echo there. So the system dynamics model is definitely the way to go, so that we can understand the intricate details at the layer level and the project level and try to look at the effects of multiple components in detail. So you can think this as more like a microstructural model in an asphalt mixture. Let's say if you're talking about a discrete element model or something that you're working with the mix versus something that you're working with the pavement. So I'm going to use a analogy here. What we are interested in is more like the network level results on the entire United States, and then multiple pavements and thousands of pavements, and how the changes would affect the overall behavior. When we do that, of course, runtime is the biggest issue. So our focus was on relying on really nice models from the literature, like the ones you mentioned. There are really nice models out there. And so we use those system dynamics models and what outputs that they can provide. And we use that in our model to as an input, in a sense, like, okay, here's a 20% reduction in resilient modulus. System dynamics shows that that's what happens in this pavement. And then for us, okay, when you have that 20% reduction on the 7,000 pavements, how that is affecting the overall behavior for all the different structures, realistic structure, real structures, real traffic, how that. So it's just that in a sense, the focus, our focus is a little bit different. So that's why we have multiple research centers to do, some research centers focus on certain aspects and other research centers complement that. So we're kind of complement to the other research centers. We do not want to go into the intricate details of those system dynamics, then our runtimes is going to increase significantly, and we can't really do the things that we want to do, things that we kind of rely on the others. So do you want to add a few more things?
Yeah, thank you, Dr. Kutay. I think it's quite impressive and comprehensive.
Did that answer your question?
Yeah, it looks like Dai has his hand up.
Okay. Yeah, next presentation. Thank you for the presentation. This is Xiongtao Dai from Minda. I think you talk about the flooding in the decreased resilient modules, which is base materials. Yeah, I agree with that. But another aspect is not only the stiffness reduced, but also the strength is reduced. So sometimes the reason I mention that, sometimes if given the weak strength base, under one heavy traffic, the whole pavement can fail. So then before we talk about the repeated damage, like the rotting and the fatigue cracking, I think we need to control the more Coulomb failure first. Just wondering, is there any reason you didn't think about that, to incorporate more Coulomb in your model?
I think that's an excellent question as well. As you know very well, more Coulomb model is a model at when you have large amount of load, and it gives you the shear failure, so impact on the shear failure. So if you have excessive load, you can have sudden failure, and obviously the more Coulomb failure envelope and changes in that envelope is going to provide that answer. Our focus is in mechanistic empirical modeling, because we are more interested in repeated loads over the design life, rather than, let's say, in just a few days of flooding, what happens in exact that few days, and when you have excessive loading. The reason is not that we don't want to do it, we don't have data to do that modeling. So you need to have sufficient information about the traffic, the load level that goes in, and that might cause a shear failure, which is directly related to the more Coulomb failure envelope. So we just don't have that kind of data. What we have is overall how much ADT is increasing because of the, let's say, the cleanup trucks or not necessarily individual. I think, as I said, that requires, which is a very important problem, that requires a focused research on what happens in these particular roads when we have X amount of loading.
Yeah, I agree with you. And the reason I'm thinking is if it's flooded, the pavement is flooded, if you have the strength criteria in the base, you can give guidance to the authority, say, during the flooding period, I can only restrict a certain vehicle pass over the pavement, because if just one heavy load pass over the pavement, the whole pavement can fail. It's no fatigue type of failure anymore. I mean, so yeah, that's what I'm thinking.
Yeah, that's a very good point. That's a very good point.
Thank you.
Go ahead.
Thank you for this comment. So what I want to add on onto that is that although that we don't have enough data for the Moore plume analysis, but in the repeated load analysis as well, we were thinking of doing some analysis to find the restricted amount of loading and restricted amount of time after flooding. Because when we are investigating the results, the rotting, fatigue cracking, and IRI, everyone, all of them, so we saw that a significant amount of jump, so the rate of the jump at the right after flooding is the highest. So the rate of the jump in the, for example, rotting distress or anything. So if you have some load restrictions, for example, let's say 10 days or 5 days, so we need to do the analysis after the flooding. So you can make sure to, control the amount of distress after flooding as well, if it is possible, of course, by the transportation network. So that's a very good question, I think.
Yeah, if you're planning to do laboratory testing, what you heard for the next for the following projects, then maybe you can do some more clone failure to get some ballpark numbers over the base.
Exactly.
For your criteria. Yeah.
Yeah. Thank you.
Yeah. Thank you.
Okay, we have a couple minutes, and there are a couple of questions we have in the chat. One is asking about the UPDAPS information and if that's available.
We finished that project literally 2 weeks ago, and we submitted all the deliverables, the reports. There are many different reports there. The one that is directly related to UPDAPS details and the equations and everything, we need to ask FHWA, see if that is something that's an interim report we can provide to public. We can ask. We also have a final report, more like with a shorter version that needs to be probably published. So that has to probably wait. But we do have papers that we published, so we can provide those papers that you can take a look at what the UPDAPS models include.
Great. I think that answers the second question about the reports that could be shared. So if you want to send me an email with those links, I'll be sure to attach them to the listing on the Research Pays Off site, and as well as the YouTube. I can add it to the description so that if anybody needs to watch it later, they can see those other reports too there.
Absolutely.
All right, we are just about at the top of the hour, so if there are no other questions, I think we will wrap up for today.
Maybe I have a question, Lauren.
I'm sorry?
I have a question.
Oh, okay, go ahead.
Very good presentation. Thank you for giving an overview of this network level tool that we can use as DOT. Question about the last few slides. That basically the message I got was like, if you build thicker asphalt pavement, then you will take care of your flooding. Makes me a little bit nervous because if you don't have a good foundation, I don't know if that's totally a good true statement. So you referenced some California results too. Is that from modeling too, or that's from actually some sections where if you increase by 20%, you are better at flooding, responding to flooding?
Yeah, I think one thing we realized that with the California was responding to the simulations better in a sense. Although there is more flooding there, their performance is a little bit better. And then when we looked at the data, overall, their pavements are thicker by on average 2 inches thicker on average. So on average, 2 inches thicker. So that might be the reason for California. For increasing the thickness helps in spreading the load a little bit. You can think about like a snowshoe type thing, you know. So, you know, of course, the downside is you might have a heavier pavement above. So that we have, I mean, I don't think there's a model there that considers that much. This is modeling, not necessarily like a field study of actual data. But one thing that I'd like to mention, I'd like to emphasize what Farhad said is the use of geosynthetics in the unbound layers. I think that's something that we have been working on. There's a UTC project. So we would like to investigate that further, because increasing the thickness may be expensive and also may not be the best idea ever. But improving the properties of the unbound layers, let's say putting geogrids in there or some other geosynthetics and put them in the right locations, all that might be a less expensive and more reasonable solution.
Thank you.
Thanks, Raul, for the question. Good to see you.
All right. Well, one last call for any other questions. I see a few comments in the chat. Thanking you again for your presentation. I think we will wrap it up for today. So thank you to Dr. Emin and Farhad for their presentation and their time this morning. And thank you to all of you for joining us. I know it was a last minute invitation, even though we've been talking about this for a few months, that it was on the books. So I apologize for the last minute official invitation. But thank you for joining us, and we will see you in 2024 in February for the next Research Pays Off. Hope everyone has great holidays and a Happy New Year.
Thank you.
Thank you. Bye, everyone.